Dear students, now we are going to discuss the derivation of the condensation for the vertical plate. Now consider this vertical plate on which the condensation of the vapors is taking place. This is a vertical plate and on the temperature is Ts or the temperature T surrounding this plate on one side, and on the another side of this plate the vapor temperature, that is the T saturation temperature, that is observed. B, that is the width of this plate. B, that is the width of this plate. So you can imagine that this is the plate which is on one side of this plate, the temperature below the saturation temperature is available, and on the another side the vapors that is available. So vapors will get condensed because on this another side the temperature is lower. So the vapors are bound to get condensed. So that is going to condense on this surface. Now B is the width of this plate. Then temperature on one side, that is the T, and temperature of the vapors on the another side. Now whatever the vapor that is getting condensed at this point, that is going to form a liquid film. That is going to form a liquid film on this solid surface. And at the top there is a very less vapors that is condensing, and as the condensed vapor rolls down, condensed liquid rolls down, the new additional vapor that is also getting condensed. So this new additional vapors which is getting condensed at this point adds or accumulates to the rolling fluid from the top, and that is why your delta increases from top to bottom. The direction considered is the y in this derivation. Then the heat transfer resistance because of this plate, that is neglected. The temperature of the surface Ts this is the Ts and this is the T saturation. Vapor temperature is the T saturation temperature and Ts is the surface temperature. Ts is the surface temperature. So the resistance because of this metal plate is neglected, and so the inside temperature of this plate, that is also assumed to be the Ts. Then the film is in good contact with the solid surface, so the temperature inside the film is uniform. That is also second assumption. The temperature at the outer surface of the film is the Ts. Then your thermal conductivity, viscosity, density of the condensate film is independent of this temperature. Then vapors on condensation gives only the latent heat. That is one important consideration. Vapors, these vapors, they only give the latent heat. That is, it will be at a same temperature. If the water vapor that is at 100 degrees Celsius is there, you will get the condensate also at 100 degrees Celsius. That is why the vapors only gives the latent heat. No change in the temperature of the condensing liquid that is observed. So liquid mass influenced by the viscous shear and the gravitational force. Now, so this liquid mass which is getting moving down, that is influenced by the shear forces and the gravitational force. Because of this gravity, this liquid is moving down, liquid film that is moving down. Now, consider a small element A and analyze it for the force balance, and second is the mass balance. First we will analyze the force balance. Whatever the shear stresses is because of the resistance offered by the viscosity. The viscous shear stresses, which is fluid which is rolling down, that is offering a internal resistance, is because of the viscous forces. Now viscous shear stresses at y, which is given at tau, which is given as mu into du upon dy, mu into du upon dy, that is your viscous forces. And on the another side, the viscous forces will be the mu du upon dy plus mu into d2y upon dy square. So the viscous shear stresses at the y, which is mu into du upon dy, and the viscous shear stresses at y plus dy, that is mu into du upon dy plus mu d2u upon dy square. Y is this direction. Y is this direction, that is in the delta direction, and x is the vertical direction. This is the x and this is the y in this derivation. You have to remember that x and y notations are different. Now there are different derivations associated or interlinked. One is related to the velocity distribution, then the mass flow rate, then the heat flux, and the heat transfer coefficient. The four things we are going to discuss: velocity distribution, mass flow rate, heat flux, and the heat transfer coefficient. So one by one we will see. Then second is the gravitational force on this element. Because of the gravity, this fluid is moving downwards, and this gravitational force is rho g into the volume. B is the width, dx and dy is your direction. So similarly also, to manage the units, you are multiplying the shear stress mu into du upon dy by the volume and by the area, b dx, and this is the change that is going to observe multiplied by the b dx, that is the area. So equating the gravitational force, which is equal to the net shear force. So the gravitational force is nothing but rho g into the volume, which is equal to the net shear force. The force in the y direction from the wall towards the another end. Force in this direction and which is moving out from this element. That is mu into du upon dy plus mu into d2u by dy square into b dx, which is on simplification you will get d2u upon dy square, which is equal to minus rho g upon mu. Now integrating this twice and substituting the boundary conditions. After integrating, first du upon dy, which is equal to minus rho g into mu into the y plus c1, and u, which is equal to minus rho g upon mu into the y2 upon 2 plus c1y plus c2. Then the boundary conditions at velocity will be 0 at y equals to 0. At this stop point, velocity is 0, where y that is equal to the 0. That means at the surface, at this surface which is in this y direction, velocity of the fluid around this metal plate will be considered to be the 0. So u that is equals to 0 at y equals to 0. And second is change in velocity in the y direction is taken as the 0 at y equals to delta. So y equals to delta is this outer surface of the film. So change in velocity in the y direction, change in velocity in this y direction is 0 on this surface. There is no gradient in the velocity in this y direction. At this wall it is velocity is 0, but the change in velocity in this direction at this point and on the outer surface of the film, that is the 0, outer surface of the film, that is y equals to delta. So change in velocity in the y direction is taken as 0. So substituting the values, you will get C2 that is equal to 0 and C1 which is equal to rho g upon mu into the delta. Then velocity distribution, substituting the values of C1 and C2, you will get this equation. So u, which is equal to the rho g upon mu into delta y minus y square upon 2. The mean flow velocity is to be calculated there. Mean flow velocity of a liquid film at a distance x, at a distance x, x is a vertical distance from the top. So that is 0 to delta u bar, that is the mean flow velocity. U bar is the mean flow velocity from 1 upon delta, from 0 to delta u into dy. So you are substituting this u and integrating it, so that you will get u which is equal to the rho g delta square upon 3 mu. Rho g delta square upon 3 mu. This is what the velocity u you will get. Now the mass flow rate calculations. The amount of liquid flowing down at any point x over the thickness delta. This is at any point x over the thickness delta. So इस x point पे कितना mass flow rate है, that is what we have calculated the velocity at a distance x, and with this delta thickness, so mass flow rate, which is equal to the mean flow velocity into the flow area into the density. Mean flow velocity, flow area into the density, that is going to give you the mass flow rate. For increase of the m, differentiate this dm, d upon d delta. You get this gb rho square delta square upon mu into the d delta. The next is the heat flux. Heat which is getting transferred through this liquid film. जो कुछ हीट ट्रांसफर हो रही है वो लिक्विड फिल्म में से हीट ट्रांसफर हो रही है, and that is because of the conducted surface, you can say. The heat flow rate into the film, which is equal to the dq, which is equal to the energy released due to the condensation, that is the lambda, that is the latent heat of condensation. Heat flow rate into the film. When you talk into the film, so mass flow rate of that film, that will be there, and the latent heat of condensation, m lambda, q, which is equal to m lambda. So whatever the heat that is getting transferred is the q, which is equal to the m lambda. So we are assuming or doing the calculation in the small volume element or small element A. So dq, which is equal to dm into the lambda, that simplifies to this. And whatever the heat that is transferred into the film is getting conducted through the film. Nusselts assume that this heat is conducted through the film. So this is the vapors that is getting condensed, and this is conducted through the film. The two different things are there. Vapors से liquid film में आ रहा है, and through the liquid film to the metal wall. So vapors are getting condensed is the dq, which is equal to m lambda, and it is conducted through the film. It is because of the conduction, that is Ka delta T upon delta X. So delta X in this is the width, thickness. So it becomes your thickness of the liquid film. K, and area of cross section of the liquid film is B into the dx. B is nothing but the width. B into the dx. ये surface area है, and the thickness is in this way. So that is the temperature gradient is T saturation to the Ts. So equating these two equations, that is the heat lost by the vapors because of losing the latent heat is getting transferred through the liquid film, so they can be equated. And after simplification, you will get this equation, and integrating it with the d delta, you will get this equation for delta which is equal to 0 at x equals to 0. At x equals to 0, that means at the top, at the x equals to 0, that is your top point. Velocity is also velocity will be there, thickness will be 0. So C that comes as the 0, and delta on simplification raised to the 4k mu into Ts T saturated minus the T wall temperature into the x upon rho square g into the lambda raised to the 1/4. So the film thickness increases as the fourth root of this distance. That is, the film thickness increases at the fourth root of the distance. The next is the film heat transfer coefficient. So H that is there. Through the conducted through the film, we have for the film conduction through the liquid film, and this can be also expressed in terms of the heat transfer coefficient, convection. So dq, which is equal to H into the B dx into T saturated minus Ts. So these two equations, they can be equated. So Hx, which is equal to K upon delta. So this H heat transfer coefficient, that depends on the thermal conductivity of the fluid and the thickness. As the thickness increases, your heat transfer coefficient decreases. So substituting the value of delta in the above equation, Hx, which is equal to K upon delta. So x, which is at a distance x, you can substitute this is hx at a distance L, this becomes HL, and this x becomes equal to the L. So the rate is high at the top. Maximum rate you will get, maximum rate of the heat transfer you will get at the top of this film, because there is the zero thickness is there, and you will get the maximum temperature gradient also there. Then by integrating this local value of the Hx over the entire length, so H average, which is equal to 1 upon L from 0 to L, Hx into the dx. So H average, which is equal to the 1 upon L 0 to L into the delta. On simplification, you will get this as the 4 upon 3 HL, or H average, which is equal to 0.943 into K cube rho square G into lambda upon mu L into 2 saturated minus Ts raised to the 0.25. This is very important equation. You have to remember this heat transfer coefficient for the entire surface for the length L. Now the Hx, and this is the plate height. The heat transfer coefficient at the top edge is maximum. At the top, heat transfer is maximum and it goes on decreasing. And the film thickness, this is the plate height. इसको अपन rotate कर देंगे then. So this is what the plate height. This is the plate height that is there. So at this distance dx, the film thickness increases. So give the result. Now this equation, the above equation, gives the result lower than the actually obtained. So the 20% increase is there. So this is multiplied by 20% and you will get 1.13. So this is h bar, which is 1.13 into k cube rho square g into lambda upon mu l into T saturated minus Ts raised to 0.25. So Q, which is equal to the h bar A into T saturated minus Ts, and M, which is equal to Q upon lambda. Now if it is a horizontal tubes, it's a vertical tube that is having the factor of 0.943 for vertical tube or vertical plate. This derivation is 0.943. And if the tubes are horizontal and for the film wise condensation, the same derivation that is obtained, but the constant is different, that is 0.725 k cube rho square g lambda upon do into mu into Ts minus T. Here you have to remember that this is the do because the condensation is taking place on the outer surface. Here the length L that is to be taken into account, and here the do outer diameter that is to be taken into account. For a vertical bond of horizontal tubes with end tubes directly placed one over the another in the vertical direction, that is the banks of a tube, vertical tubes, they are placed one over the another. So here N that is taken, N is the vertical rows of the horizontal tube, vertical rows of the horizontal tubes. That means if there are 100 tubes in the square arrangement, 100 tubes are there on this plate, there are 100 tubes, 1 2 3 4 5 6 7 8 10, like this, 10 tubes and 10 rows, 10 columns and 10 rows are there. So whatever the vertical number of tubes, so for 100 tubes in square array you will get 10, which is equal to the N. So this N that becomes 10. This is for the vertical rows of the horizontal tube. And if it's an array of 16 tubes, that is 4 by 4 tubes that is available, then N that becomes equals to the 4. Then the dimensionless form of the Nusselt's equation for the vertical tube, that is H into mu square k cube rho square g raised to the 1/3, which is equal to 1047 4 m upon mu raised to the 1/3. And similarly for horizontal tube, this is there.